Okay, so let me share my screen. And we're going to continue our discussion of chapter 2. In fact, um, only one, whoops, only one thing I need to cover, one topic, and that is acids and bases. We're going to learn about a couple of definitions, and then we're going to look at how we name acids and bases. All right, so it turns out that there are several definitions that is used in chemistry for acids and bases. Hold on, see a couple of messages here. Okay, so yes, I was saying there are a couple of definitions that is used in chemistry when it comes to acids and bases. The ones that we'll be focusing on now is the definitions as put forward by this guy by the name of Arrhenius, all right? And for those of you who plan to do Chem 2, you're going to learn that there are two other definitions that are used in chemistry, all right? And there are more actually, but there are two more definitions that is used in chemistry that you'll learn about in Gen Chem 2, right? But for now, we're just going to stick to the Arrhenius definition, right? And according to Arrhenius, an acid is a substance which, when added to water, produces hydrogen ions and an anion, all right? So that's what an acid is. According to Arrhenius. And then according to Arrhenius, a base is a substance which, when added to water, ionizes and produces hydroxide ions in solution and some cation being formed also, all right? So that's a definition of the Arrhenius acid and Arrhenius base. Now, you can have a reaction between an acid and a base. That reaction is called neutralization. And basically, the result of that reaction is the formation of water and a compound known as a salt. And the salt composition and structure is based on the acid and base that you use, right? In fact, the salt is a combination of the cation, which comes from the base, and the anion, which comes from the acid, all right? So that's basically what a salt is. And later on, we're going to look at neutralization reactions in more detail, all right? So here is basically a list of acids and their names. Now, what I'm going to get into, and this will complete this chapter, is how do we go about naming acids, right? So let me get out of this here, and let me open up a Word document here. And okay, so the first type of acids, there are two broad categories of acids, right? The first type of acid, they are known as binary acids. What's going on here? Okay, so binary acids, right? And binary acids are basically acids which is made up of hydrogen, a combination of hydrogen and another element which is a nonmetal. All right? So that's what binary acids are, a combination, chemical combination of hydrogen and a nonmetallic element, all right? And that's it. So the only two elements present, one is hydrogen and the other one is nonmetallic, all right? Now, I think I mentioned this before, but I remember saying that one of the exceptions of the nomenclature rules when it comes to naming binary molecular compounds is where you have hydrogen bonded to another element, right? And if you remember, I said that in those cases, you do not use prefixes, right? So for example, HCl, which is simply known as hydrogen chloride, all right, for example, all right? Or, just use another example, H2S is known as hydrogen sulfides, right? So when naming these compounds, binary hydrogen-containing compounds, we do not use prefixes in their names, all right? Now, the thing about these compounds is that they're usually gases. In fact, I can't think of any such compound where it's not a gas, right? Now, basically, we can form a binary acid by adding these gases to water, right? So basically, you're going to end up with HCl gaseous converted to HCl aqueous, all right? So when we have this, now this is basically an acidic solution. And therefore, in this form, the name of this compound is hydrochloric acid. All right? So just to briefly describe how we get the name, for naming binary acids, they all start off with hydro, right? And then you have chlor, which is the stem of the name of the other element. And then it ends with ic acid, right? And that is basically the format that you would use to name binary acids. Hydro, then the stem of the name of the other element, then ic acid, all right? So applying that to this example, again, you add to water, and you're going to get your acid, H2S, aqueous. So the name of this compound is hydrosulfuric acid. All right. So again, it's hydro, then sulfur, which is basically the name of the other element in this case, and then ic acid. So that's basically how we name binary acids. Hydro, the stem of the name of the other element, and then ic acid. All right. Okay, so that's how we name binary acids. Now, the other broad group of acids are known as oxoacids, all right? And they're called oxoacid because they contain oxygens, right? So let me erase this here. Okay, so just to give you one or two examples of oxoacids, HNO2, that's an oxoacid that is known as nitrous acid. All right. Now, how do we arrive at the name of this acid? All right. There are a couple of approaches you can take. The one that I prefer to take is that I look at the formula for the corresponding anion, in which case that would be the NO2 minus ion. All right. And the name of this anion, you can identify it in the tables that I've provided for you. We call this the nitrite ion. All right. Now, according to the IUPAC rules, if the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS acid. All right. So nitrite, which can be converted to HNO2 by adding an H plus ion, will be converted to nitrous acid. All right. So here's another example. SO3 2 minus, right? In this case, it's called the sulfite ion. And if you add, in this case, two H pluses, now, in this case, you need to add two H pluses because you have a negative 2 charge here. So you're going to end up with H2SO3. And therefore, the name of this acid is sulfurous acid. So again, as you can see, the ending of the anion is ITE. And therefore, the ending of the corresponding acid name is OUS acid. All right? So that's how you name these acids, right? According to the name of the anion from which they're formed. All right? Now, there are some other anions whose name ends with not ITE, excuse me, but ATE. So let me delete all this here. So one example of that would be the nitrate ion, which has the formula NO3 minus. So this is called nitrate. So to convert this to the corresponding acid, we add one H plus because there's one negative charge here. So this becomes HNO3 in terms of the formula. And the name of this acid will be nitric acid. All right. So you'll notice that the difference here compared to what we just looked at, in this case, the name of the anion ends with ATE, which means that the name, excuse me, of the acid ends with ic acid. All right. So, excuse me. Sorry about that. So if the name of the anion ends with ATE, the name of the acid that is formed from it ends with ic acid. Now, here's another example, SO4 2 minus. In this case, you need to add 2H plus to get H2SO4. The name of this anion is the sulfate ion. The name of the corresponding acid is sulfuric acid. All right. So that's basically how we name acids based on the names of the anions that end with ATE. If the name of the anion ends with ATE, then to get the name of the corresponding acid, we replace the ATE ending with ic acid. If the name of the anion ends with ITE, then you replace the name or the ITE ending with OUS acid to get the corresponding name of the acid that is formed from it, all right? So that's basically how we name acids. Now, there's one more thing I want to mention here, and that is there's one particular compound which is kind of unique in terms of not belonging to any one of these two categories. Because remember, we talked about binary acids and we talked about oxyacids. Now, there's one particular acid. Let me write down the formula here. That is HCN aqueous, right? Now, if you look at this acid in terms of the formula, you can see clearly it's not binary because there are 3 atoms, right? And it's also not an oxyacid because there's no oxygen present. So basically, this is kind of unique in terms of, the category that one cannot put it in based on the definitions I gave you earlier. So what IUPAC decided to do, as far as this is concerned, is that they treat HCN as a binary compound for the purposes of naming this compound. So if you do that, this is a gas, by the way, and the name of this compound is hydrogen cyanide. Hydrogen cyanide. So as you can see, the name is in the fashion of that of a binary compound, even though it's not, right? But, or not but, and when you add it to water, it forms the acid, and the name of the acid is hydrocyanic acid, which again is in the form of a binary acid in terms of the name. But as we said before, we all know it's not a binary acid, right? So basically, this is a different, unique type of situation. And therefore, what IUPAC decided to do was to basically treat it for the purposes of naming as a binary acid, all right? Okay, so that's basically it as far as I can see for this chapter. Let me just check something here. So, oh, by the way, so this list I showed you earlier, all the rules that we talked about, you can see it at work in this list. So they gave you some examples of acids here, and you can see based on the rules I just described, the names are given. So for example, HCl, H2S, H2S, and I think that's it. Those are binary acids. And you'll notice that they both start with hydro, and then the stem of the name of the other element, and then ic acid, right? And then if the acid, if the anion name ends with ITE, then the corresponding acid ends with OUS. So you see that here in the case of hypochlorous, chlorus, and hypochlorous, and sulfurous and nitrous, and so on. And then if the name of the anion ends with ATE, then the corresponding name of the acid ends with ic acid. And you see that here with chloric, perchloric, sulfuric, nitric, phosphoric, and carbonic, all right? So that's basically how the rules for naming acids work, all right? So that's pretty much it, all right, for this chapter. So based on this that we have done, you now should be able to complete, let me just check something here, all of assignment number 2. Let me just do a quick look at it. Okay, let me just do a quick perusal of number 2. Okay, so now, right. I remember I told you guys to stop at number 12, right? So now you should be able to do number 13. And let me see here. 14, 15, 16, because we did hydrates already. And then 17. Okay, so yes, you should be able to complete this assignment. So what I'm going to do now is I'm going to open up the Dropbox for that assignment, assignment number 2. And I'm going to, okay, so today is what? The 5th? Okay, I'm going to let it be due on Monday. All right. So let me set these dates. Okay, so now you are able to upload it into Canvas. So that's when it's due. All right. So what I'm going to do right now is move on to the next chapter, which deals with, again, a topic that you would have encountered in your introductory chemistry course. So again, I'm going to go through this rather quickly, and that is stoichiometry. And just to remind you what stoichiometry is all about, stoichiometry is that area in chemistry which is concerned with the quantitative relationships between different substances involved in a chemical reaction. And there are some things that you have to basically have a fundamental understanding of, things like the concept of balancing equations and what it means, right? Very important skill for you to master because for most stoichiometric problems, you would not be able to solve these problems unless you start off with a balanced equation. In some cases, you may be given a question where the equation is already balanced, in which case you don't need to balance it. But in other cases, you may be given an equation which is not balanced, and therefore you have to balance it before you can do the rest of the problem. And yet in other cases, you might be given a question which is described in words, and therefore in terms of the reaction. And therefore what you'd have to do is, based on the information provided, figure out what the balance equation is before you can do the stoichiometric problem. So that's what we'll be talking about in this chapter. So we have to cover some fundamentals. I think we discussed this earlier. Molecular mass, what that means is basically the sum of the atomic masses of the atoms represented in a molecular formula. Now, this applies to molecular compounds, right? There's another term which we apply to ionic compounds, and that is called the formula mass, right? And that is based on the formula for the ionic compound, right? But basically, it's the same thing as in the case of what the molecular mass is. Based on the formula, in the case of an ionic compound, you simply add up all the atomic masses of the different elements present, as described in the formula, all right? Now, of course, you need to recognize that ionic compounds do not have discrete units. We talked about that already, right? So basically, in terms of what the formula represents, we call that a formula unit, right? The formula unit is something that's kind of analogous to molecular formulas, or molecules, I should say, all right? Okay, so if you're asked a question like this, calculate the formula mass of ammonium sulfate, which is a fertilizer commonly used by home gardeners. The first thing you have to find out is, what is the formula of ammonium sulfate? So can anybody tell me how you determine the formula for ammonium sulfate? Let me give you a hint. You may find the table that I've provided in Canvas for you quite useful. The table of common ions.
So we'd have to find the charge of the ammonium ion.
Exactly. Oops, this is. So what's the formula for the ammonium ion?
NH4 plus.
NH4 plus. And what's the formula for the sulfate ion?
SO4 2 negative.
Okay. So how do we put this together to get the formula for the compound?
In order to neutralize it, we'd need 2 of the ammoniums.
Exactly. So what would be the final formula?
NH4 in parentheses.
Exactly.
Subscript 2. Sulfate SO4.
Exactly. So that's what you need to do first before you can determine what the formula mass is. So to get the formula mass, we have to look up the atomic masses of the different elements and add them up according to the formula, right? So based on the formula here, I see that there are two nitrogens. So I'll take two, this is happening. I will take 2 multiplied by the molar mass of nitrogen, which is, if I remember correctly, 14.01 AMU. And then I would add that to 2 times 4, 8 hydrogens times 1.008 AMU. And then I would add sulfur. If I remember correctly, sulfur is 32.07 AMU. And then the 4 oxygens, 4 times 16.00 AMU. All right? So let me get my calculator. Okay, so 14.01 times 2. So, and then I'm going to add that to 8 times 1.008. And then I'm going to add that to 32.07. And then I'm going to add that to 4 times 16. And according to my calculation, and please tell me if I'm wrong, I'm always willing to be corrected, but I got 132.15 AMU as the answer. All right? So that's basically how that is done. All right? Any questions about this? Any questions? Any questions? Okay, so here are some other terms that you should be familiar with: the mole concept and Avogadro's number. So basically, I'm quite sure you're familiar with counting terms. Like, for example, everybody knows that 1 dozen is equal to 12 items, right? So I like to see the Avogadro's number as a counting term that we use in chemistry and physics, right? The difference, of course, that, the mole, which is what Avogadro's number represent, is not 12. It's a much larger number, right? And that's what Avogadro's numbers is. And that's because when it comes to measuring the amount of particular substance, when you consider the number of particles present, atoms, ions, and so on, that's a very huge number, right? So the mole is, the definition here, is the amount of substance that contains as many elementary entities as there are carbon atoms in exactly 12 grams of the carbon-12 isotope, right? And the number here, which is Avogadro's number, is 6.02 times 10 to the 23 moles to the minus 1, right? So this would represent the number of items in 1 mole, right? Now, this can be applied to literally anything, right? You can have 1 mole of oranges, 1 mole of chairs, 1 mole of human beings and all that. But in chemistry and physics, we use it with respect to atoms, ions, and so on, those small particles, because those numbers are usually very huge for the type of calculations that we normally do, all right? So just to give an idea as to how large a number this is, as stated here, 1 mole of oranges would weigh as much as the mass of Earth. So that gives you an idea as to how large that number is. And one key thing I need to mention here, when it comes to abbreviation of the mole unit, we do not use uppercase M or lowercase m, and that's because you want to avoid confusion. Uppercase M is the unit of mole per liter, which we're going to talk about later on. And lowercase m can represent either meters in terms of unit of length, or another unit of concentration, which is molality, which you will not be using in this semester. But again, for those of you who have to do Chem 2, you will certainly encounter that unit, all right? So normally, and this is not much of an abbreviation anyway, normally when you want to abbreviate the mole unit, in most textbooks, you're going to see something like, you're going to see MOL, which is not much of an abbreviation when compared to MOLE, but that's basically the standard conventional abbreviation of the mole unit. Okay, now, one interesting thing about the mole unit is that you can actually look at the amount of different substances present, or I should say the amount of different elements present in a compound, and establish a relationship between the moles of the different elements based on the formula, right? So to illustrate that fact, let's look at this relationship between carbon and oxygen to form carbon dioxide, right? So basically, this is the equation for the reaction. One carbon atom will react with one oxygen molecule to form one carbon dioxide molecule, right? So if you were to extend this from 1 to 12, and 1 to 12, and 1 to 12 here, you see the same relationship. In other words, 1 dozen, 12 carbon atoms, will react with 12 oxygen atoms or oxygen molecules to form 12 carbon dioxide molecules. So if you increase the amounts proportionally to Avogadro's number, which is, again, that very huge number, 6.02 times 10 to the 23 atoms of carbon will react with the same number of atoms of oxygen molecules to produce the same number of carbon dioxide molecules, right? So basically what we're saying here is that while this is true, that one atom of carbon will react with one molecule of oxygen to form one carbon dioxide molecule, it is also true that 1 mole of carbon will react with 1 mole of oxygen to form 1 mole of carbon dioxide. So basically, if you're given a balanced equation for a reaction, the coefficients associated with the different substances not only represent the ratio of atoms to molecules or whatever, it also represents the mole ratio relationship between the different substances involved. And we can exploit that relationship to do certain calculations. For example, if you're given a certain amount of reactants, you can determine how much product you can get, or vice versa, all right? Another thing I want to point out here is that 1 mole of a substance does not necessarily mean, and in fact is very unlikely to mean, that 1 mole of one substance would be equal to, in mass, a mole of another substance. Different substances can have, and more than likely will have, different masses per mole, all right? And that is demonstrated here, because it turns out that in the case of carbon, 1 mole of carbon atoms will have this mass here, 1 mole of oxygen atoms will have this mass here, right? So clearly there's a difference in masses here, and the same is true on this side with the carbon dioxide, right? So that's one important thing. In fact, we're going to talk about molar mass, I think, in the next slide following this one. But before we leave this, one other thing I want to point out, and that is that this here illustrates, again, the conservation of mass law, right? If you remember, the conservation of mass law says that in a chemical reaction, matter is not created nor destroyed. And one can see that clearly in this example, because if you take the total mass of the reactants here, the 12.011 plus the 31.9988, if you add them together, you see that it's equal to the 44.010 grams of the carbon dioxide on the other side. So that illustrates the conservation of mass law. And the reason why that law is true is because there's no destruction or creation of atoms as you go from one element or one side of the reaction to the next, as you go from reactants to products, all right? Okay, so this is just illustrating what I just said a while ago. 1 mole of an element, for example, would be different from another mole of another element in terms of the mass. So what we're looking at here is a mole of sulfur, a mole of copper, a mole of mercury, and a mole of helium, right? And clearly, these are different substances, and they will have different masses, right? So to answer this question, how many atoms of helium are present, of sulfur, of copper, of mercury? The answer is the same for all of them, which is Avogadro's number, 6.02 times 10 to the 23. The difference, however, will be in the masses. So this leads us now to the concept of molar masses, right? Or molar mass. What's the definition of molar mass? The molar mass of a substance is the mass, usually expressed in grams, of 1 mole of that substance. And that substance could be an element, it could be a molecular compound, it could be an ionic compound, all right? So that's what the molar mass is by definition. And the units of molar mass, I don't think I have it here on this PowerPoint. So let me write it here. The unit of molar mass is grams per mole. All right, that's the unit of molar mass. All right. So what you'll find is that it turns out that the actual molar mass value is numerically equal to the atomic mass if you're dealing with elements, or the molecular mass if you're dealing with molecules, or the formula mass if you're dealing with ions, right? So for example, sodium, if you consult the periodic table, you see that sodium has an atomic mass of 22.99 AMU, right? Well, the molar mass of sodium is 22.99 AMU. The difference, however, is that the molar mass will be expressed in grams per mole, while the atomic mass will be expressed in AMU. And I think I have some examples here. Oh, I do have it here. So this is the units of molar mass, all right? So some examples here. The aforementioned sodium, the atomic mass is 22.99 AMU, but the molar mass is 22.99 grams per mole. Same value, same numerical value, but the units are different. Here's another example. Now, this is an example of a molecule. The molecular mass of carbon dioxide is 44.01, right? But the molar mass of carbon dioxide is 44.01 grams per mole. So again, there's a difference in terms of the units, but numerically, they're the same. Here's another example. For potassium chloride, the formula mass is 74.56 AMU, but the molar mass is 74.56 grams per mole. So again, numerically the same, but the units are different, all right? Okay, so as a result of what we just discussed, we can establish relationships between the mole unit, the number of atoms or the number of formula units or the number of molecules, and also the molar mass, right? And this is an example using sodium. So 1 mole of sodium is equivalent to 6.02 times 10 to the 23 sodium atoms, which of course is Avogadro's number, which is itself equal to 22.99 grams of sodium. So we have those relationships. And therefore, we can write down conversion factors for any two of these three terms, right? So for example, the conversion factor relating the mole of sodium to the grams of sodium can be expressed as this or this, and whichever you use is dependent on what type of calculation that you're trying to perform. Or you have the relationship here between the mole unit and the number of sodium atoms, and it can be expressed as this, or you can invert it to get another conversion factor. And again, which one you use is dependent on the type of calculation you're trying to perform. And you can also have a conversion factor which relates the mass in grams to Avogadro's number, right? And again, you can have it one way or the other in terms of what's in the numerator and what's in the denominator, all right? And of course, as always, and I'm quite sure you would have discovered this when you were doing introductory chemistry, that sometimes some preliminary and calculations following the conversions would be necessary, again, depending on what question you're dealing with or what you're asked of to do, all right? Okay, another thing I want to point out here is that based on the amount of moles of a particular substance and the formula, you can determine the moles of the different atoms of each element present. Now, what we're looking at here is a situation where we're assuming that we have 1 mole of these two substances. So let's look at the one to the left. And basically, if we're starting off with 1 mole of molecules of this compound, right? We can, based on that fact, determine the number of moles of the different elements present. So because you have a subscript of 3 here, we can say that 1 mole of this compound contains 3 moles of carbon atoms. We can also say it contains 8 moles of hydrogen, and we can also say it contains 3 moles of oxygen atoms, all right? So that's basically how we can look at determining the number of moles of the different atoms of the different elements based on the molecular formula. Here's a more complex example, but the same principle applies. So this is the formula for ammonium sulfate. If we have 1 mole of ammonium sulfate present, then we can determine the number of moles of the different elements. Now, in this case here, we can break this down to look at the number of moles of ammonium ions. That tells you that you have 2 moles of ammonium ions. And basically, we can break this down further because based on the formula here, we can say that we have 2 moles of nitrogen and 8 moles of hydrogen present, right? And then as far as the sulfur is concerned, or the sulfate is concerned, there's 1 mole of sulfate present in 1 mole of the compound. And then we can break this down further to say that 1 mole of sulfate ions will contain 1 mole of sulfur atoms and 4 moles of oxygen atoms. And that's basically how that is done, all right? So this idea you're going to find useful, especially when it comes to solving certain problems in assignment number 3. Okay, any questions so far? Any questions? Any questions? No questions? All right. So let's look at some examples. Now, what I'm going to do is copy this here and post it in Word. Okay. So this question, actually, it's a series of questions, but the first one is asking for you to determine the mass of a 0.050 mole of sample of sodium. Okay, so basically what this question is asking for, well, the question gave you 0.0, this is A, 0.0750 moles of sodium, and you're asked to determine the mass in grams of sodium. All right? So let's start off with what we were given, 0.075 moles of sodium, and then we're going to multiply that by a conversion factor which allows us to convert from moles to grams, right? And we know the relationship between grams and moles would be the molar mass. So you go to the periodic table, you look at the molar mass of sodium, and you see that it's 22.99 grams per mole. And the way you represent that here is that you're going to put 22.99 grams over 1 mole of sodium, so that this cancels out with that, and then we just do the multiplication, 0.0750 times 22.99. And according to my calculation, you have to round this out to 3 sig fig because this should be a 0 here. So according to my calculation, this would be 1.72 grams of sodium, and that would be the answer for A. All right? Any questions about this? Any questions? Okay, the next one, they gave you the mass of sodium, right? They gave you 62.5 grams of sodium, and they're asking for the moles of sodium. So this is the reverse of what we just did. So we're going to start off with 62.5 grams of sodium. So my question to you is, what would be in the conversion factor here? In other words, what would be in the numerator and what would be in the denominator? So what say you?
Going to be the grams in the denominator.
Okay, so the grams will be down here, and the moles of sodium would be above. So what would be the numbers?
1 mole of sodium over 22.99.
Exactly. So let's see what that gives. So 62.5 divided by 22.99. And according to my calculation, I got 2.72 grams of sodium. All right? And that's how that is done. All right? Any questions about this? Any questions? Okay, the next one is, let's clear this here, the C part, which says, the mass of a sample of sodium containing 1.00 times 10 to the 25 sodium atoms. So basically, 1.00 times 10 to the 25 sodium atoms. And we need to find out the mass, presumably in grams of sodium. All right? So how do you think we would tackle this? We're going to start off with 1.00 times 10 to the 25 sodium atoms, right? So how would you tackle this? What would you multiply this by?
Transfer it by the number, Avogadro's number into moles, and then moles into grams.
Okay, so, all right, very good. So in other words, you're suggesting 2 conversion factors, right?
Yeah.
So what would be the first conversion factor? What would go down here and what would go up top here?
Avogadro's number on
Okay,
the denominator.
6.02 times 10 to the 23 sodium atoms. Okay, and what goes up top?
1 mole.
1 mole of sodium. All right, so that this goes with that. Okay, and then now the next conversion factor would be
the denominator would be 1 mole of sodium
Mhm.
and the numerator would be 22.99.
Okay, so let's see what that gives. 1 times 10 to the 25, oops, wrong number. 1 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.99. And according to my calculation, now this would have to be rounded off to 3 sig figs, which means that the answer would be 382 grams of sodium. And that's how that is done. All right? Any questions about this one? Any questions? Okay, so now we are going to move on to the D part of the question. And the D part is asking for the mass of a single sodium atom. Now that's interesting. How would we calculate the mass of a single sodium atom? Well, there are a couple of things that you have to consider when doing this problem, right? The first thing we need is the molar mass, right? Which is equal to 22.99 grams per mole. The other thing that we need to remember is Avogadro's number. Which is equal to 6.02 times 10 to the 23 sodium atoms per mole, right? So therefore, to get the mass of a single sodium atom, what we have to do is take this number, which is the mass per mole, divided by this number, which is the number of atoms per mole, right? So we're going to end up with 22.99 grams per mole divided by 6.02 times 10 to the 23 atoms per mole. The mole units will cancel out. So whatever answer you get would be expressed as grams per atom, which is what the question is asking for. So 22.99 divided by 6.02 times 10 to the 23. And according to my calculation, this works out to be equal to 3.82 times 10 to the minus 23 grams per sodium atom. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me continue with the PowerPoint. Okay, let's talk about mass percent composition. All right, again, this is something you should have met before. But basically, the mass percent composition is basically talking about the percent by mass of each element present in a compound, right? So if you have a compound made up of 2 or more elements, basically you're trying to find the mass of each element per 100 grams of the compound. So one way of calculating it for each element is using the formula that you see here. The percentage of a particular element will be equal to the mass of the element in 100 grams of the compound. Or another way of expressing it is the mass of the element itself divided by the mass of the compound times 100%. All right, so you can use either one of those two formulas. They both basically are different ways of saying the same thing. All right, so it's relatively easy to determine the percent composition of each element present in a compound as long as you know what the formula is. All right, so just to illustrate how we do that, let's look at this compound butane. The formula is given, and you're asked to find the percentage of each element present. The first thing I would do is find the molar mass. Why does it always revert to red ink? Okay, so the first thing you do is find the molar mass of butane, right? So this is the formula. So 4 times 12.01 AMU, or grams per mole, plus 10 times 1.008 grams per mole, all right? And then we do the number crunching. 12.01 times 4 plus 10 times 1.008. And according to my calculation, this works out to be equal to 58.12 grams per mole, right? Now, to get the percentage of carbon present, we simply take this portion here for carbon, 4 times 12.01 grams per mole, and divide it by the total molar mass, which is 58.12 grams per mole. And then we multiply all of that by 100%. So let's see what that gives. 4 times 12.01 divided by 58.12 times 100. And according to my calculation, this works out to be equal to 4 sig fig, so that's 82.66. 82.66%. All right. And then we do something similar for the hydrogen. So this is the part for the hydrogen here. So that's 10 times 1.008 grams per mole divided by the total again, which is 58.12 grams per mole, multiplied by 100%. So let's see what that gives. 10 times 1.008, bless you, and then divide that by 58.12 and times 100. And according to my calculation, this works out to give you 17 point, again, rounded off to 4 sig fig, 17.34%. All right? And that's basically it. That's how you calculate the percentage of each element present based on the formula. And let me just say that because there are only two elements here, that means that when you add up these two percentages, you should get, if not exactly 100%, you should get a number very close to 100%, right? In this case, it gives you exactly 100%, right? But in some cases, you might find that, the total may vary slightly from 100, maybe like 99.98 or something like that, all right? So that's basically how you determine the percentage of each element in a compound based on its formula, all right? Any questions about this? Any questions? Any questions? Any questions? Okay, so let's look at these examples. The first of which says you have to calculate the mass percent of each element. You know what? Let me copy and paste this into Word. Oh, somebody said something. Oops. Oh, I apologize, Ms. Anwar. I haven't been paying attention to the messages, so I'm going to try to do better as far as that is concerned. Okay, so what was I doing? Oh, I was about to copy and paste these questions onto Word. So let me just. Okay. All right. So the first question is asking for you to calculate the four significant figures, the mass percent of each element in ammonium nitrate. So again, before we can do anything else, we have to figure out the formula for ammonium nitrate. So what is the formula for ammonium nitrate? Again, you might find the tables useful for determining the formula for this compound. Yes, sir.
NH4,
Uh-huh.
NO3.
Exactly. All right. So that's a formula for ammonium nitrate. So what this question is asking for you to do is to find out the percentage of each element present in that compound to 4 sig figs, right? So let's start off with the nitrogen, right? The percentage of nitrogen would be equal to, now in this formula here, you see that there are two nitrogens. So it's 2 times the molar mass of nitrogen. Oh, before we do that, we need to add up everything first. So let me erase this here. I'm sorry. We need to add up the molar mass of ammonium nitrate first. So molar mass of NH4NO3 is equal to 2 times the molar mass of nitrogen, which is 14.01 grams per mole, plus 4 times the molar mass of hydrogen, grams per mole, plus 3 times the molar mass of oxygen, which is 16.00 grams per mole, right? And then we add them up. So let's see what this gives. 14.01 times 2. And then I'm going to add that to 4 times 1.008. And then I'm going to add that to 3 times 16. Okay, so according to my calculations, and again, please correct me if I'm wrong, I got 80.052. In fact, I should round off to 80.05. So let me take that off. And this will be grams per mole, right? Okay, so once we get that, now we can find the percentages. I'm going to start off with the nitrogen. So for the nitrogen, I'm going to take this part here, 2 times 14.01 grams per mole, and divide it by the total, which is 80.05 grams per mole, and multiply all of that by 100%. So let's see what that gives. 2 times 14.01 divided by 80.05 times 100. And according to my calculation, this works out to be 35.00%. All right? So that's for the nitrogen. And then we're going to do the same thing for the hydrogen. So that will be equal to, now this is the part for the hydrogen. So that will be 4 times 1.008 grams per mole divided by 80.05 grams per mole multiplied by 100%. And let's see what that gives. 4 times 1.008 divided by 80.05 times 100. And I got 5.0. I mean, 6. Okay, so 5.037%. And then finally, in the case of oxygen, this is the part for the oxygen. So that would be 3 times 16.00 grams per mole divided by 80.05 grams per mole times 100%. So let's see what that gives. 3 times 16 divided by 80.05 times 100. And I got, okay, again, 4 so I got 59.96%, all right? And what I would do, I always tell students to check to make sure that the total percentages add up to 100%, just to make sure that you're doing the right calculation, which I think it is. Let me do that here. 35 plus 5.037 plus 59.96. And yes, that gives you 100% when rounded off to 4 sig figs, right? So that answers what we have just done here. These are the answers to the first question. This, and this, all right? So those are the answers to the first part of, or the first example question, all right? Any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay. Let me clear. Hold on. Let me clear all this here, because I'm going to need a space. Okay, so the next question is asking, oh shoot, I erased something that I need. I'll ask you guys anyway. So the next question is asking, how many grams of nitrogen are present in 46.34 grams of ammonium nitrate? So basically, they gave you 46.34 grams of ammonium nitrate, right? Now, what I would do is use one of the answers from the previous part. I think I remember what the answer was. To establish a conversion factor that we would use to multiply the 46.34 grams by. And that conversion factor would be the percentage of nitrogen that was calculated in the first part. And if I remember correctly, that percentage was 36.00, right? Right? For nitrogen, right? So the way I would represent that here is 36.00 grams of nitrogen in 100 grams of the ammonium nitrate, right? So that this unit will cancel out with this unit, so you're left with grams of nitrogen. So all you have to do now is do the multiplication. Okay, so according to my calculations, when rounded off to 4 sig figs, the answer becomes 16.68 grams of nitrogen. And that's it, right? That's how you do the second part. All right? Any questions about this? Questions? Okay, let me move on to the PowerPoint. Y'all finished with this? All right. So let me see what next. Okay, so now we're going to get into something a bit more challenging, because what we did in terms of determining the percentages based on the formulas is relatively easy, right? What is more challenging is if you're given the percentages and you're asked to determine the formula. Now, in order for us to do that, we have to go through some steps. Firstly, we have to determine, based on the percentages, what we call the empirical formula. And again, this is something that you should have met before, right? I think I may have the definition here. No, I don't. But I think I gave you the definition earlier. The empirical formula gives you the simplest ratio of the atoms of the different elements present in a substance, right? That's the empirical formula. Now, in order for you to get to the molecular formula, which is oftentimes required from you based on the questions posed, what you'd have to do is multiply the empirical formula by a certain integer, which is called the integral factor, right? So therefore, some information would have to be provided to you in order for you to carry out that calculation. So what we're going to look at first is how we determine the empirical formula based on percentage composition data. And then later on, we're going to look at how we get from the empirical formula to the molecular formula, right? Now, to get to the empirical formula based on percentage data, what we need to do is find out the moles of each element present, right? Now, in order for us to do that, if you're given the percentage data, you have to assume that you're working with 100 grams of the substance. Because if you make that assumption, then each percentage value represents the mass per 100 grams of the substance, right? And then the next step is that you convert it to moles for each of them, and then you look at the mole ratio between the different elements present, and that would lead you to the empirical formula. So that's basically an overall description of the process. And the best way to learn it, of course, is to go directly into an example. So let's look at this example right here. What time is it, by the way? Oh, okay. I think this is where we're going to stop after completing this example. All right, so let me copy and paste this here. And let me get rid of all this here. Okay, so here's a question. You're given a compound phenol, and it gives you the composition data, percentage-wise, right? And the question is asking for you to determine the empirical formula. So as I said before, what I would do, and let me just say, I like to do this type of problem in a tabular fashion, right? So I'm going to construct a table where at the top, I'm going to put the formula for the different elements. All right? And as I said before, what we do is make an assumption that we're working with 100 grams of the compound. So basically, in this row, I'm going to put the masses, which would be basically numerically these values, but I'm going to express them in grams. So here I'm going to put 76.57 grams. Here I'm going to put 6.43 grams. And here I'm going to put 17.00 grams, right? So that's the first step. The next step is to convert each of them to moles. And by now, we all know how to do that, right? Basically, to convert from grams to moles, we divide the grams by the respective molar masses of the different elements, right? So in the case of carbon, that would be 76.57 grams multiplied by 1 mole over the molar mass of carbon, which is 12.01 grams. In the case of hydrogen, 6.43 grams. We multiply that by 1 mole over 1.008 grams. And then finally, in the case of oxygen, 17.00 grams, we multiply that by 1 mole over 16.00 grams, right? And then, oh, shoot, I shouldn't have done that. Then we work out what each of them work out to be. So in the case of carbon, that's 76.57 divided by 12.01. And according to my calculation, I got 6.376 moles, all right? That's for carbon. Do the same thing for hydrogen, 6.43 divided by 1.008. And according to my calculation, I got 6.379, all right, moles again, all right? And then finally, in the case of oxygen, that would be 17 divided by 16, and that gives, rounded off to 4 sig figs, 1.063 moles, all right? So that's how we determine the moles based on the masses. The next step is where we look at these three numbers and we decide on which one is the lowest in value, which one has the lowest mole value. And that obviously would be this. So what do we do with that? We use that to find the simplest ratio, right? And the way we find the simplest ratio is that we divide all of these values by the lowest mole value, right? Now, this one divided by itself will give you 1, right? And then we divide 6.376 moles by 1.063 moles, and then 6.379 moles divided by 1.063 moles, right? So let's see what each of these give. In the case of carbon, that would be 6.376 divided by 1.063. And according to my calculation, when rounded off to 4 sig figs, that gives you 5.998, right? In the case of hydrogen, we divide 6.379 by 1.063. And according to my calculation, this works out to be equal to 6.001, all right? So at this stage, what we'll notice is that this number here and this number here is very close to an integer. In fact, they're both very close to the same integer, right? This one is close to 6, this is close to 6, so therefore we can round this off to 6, round this off to 6, and therefore these numbers will serve as the subscripts in the empirical formula which the question is asking for, right? So therefore the empirical formula would be C6H6O. And that's it, right? And that's basically how you determine the empirical formula. Now, let me just say that there are some problems which will be a bit more complex. In fact, the next one on the same slide is a bit more complex because there's one more step that you need to perform. So we'll get to that next class, right? But for now, make sure you understand what's happening here. Now, based on what we have covered here, let me go to the files, and then assignments. Okay, so I'm going to publish assignment number 3 right now, so you can get started on that. And let me tell you up to what questions you can attempt in assignment number 3. So, okay, so in assignment number 3, you should be able to do questions 1, 2, and I would suggest you try number 3 as well. Okay, that's it. So 1, 2, 3, all right? So try those. If you have any problems, let me know, all right? One last thing. So I don't know if you saw the notice or the announcement I made. Normally I'd have office hours today in building 2, but building 2 is closed down. Some environmental problems. So as a result, I won't be in my office. Instead, I'll be online. So if you need to talk to me today or contact me, shoot me an email and then I can set up a Zoom link and then we can link up that way. All right. So that's pretty much it. Let me see who came in late, if anybody. Let me see, let me see, let me see. Barner, Davis, Jernigan is here. Osorio, Talon is here. Wilbert, and Zaradka. All right. All right, so that's it, folks. So I'll see you guys next week, Wednesday. Oh, by the way, I have some assignment 3 handouts here. So on your way out, you can pick up one.
Thank you.
No problem. Ouch.
Thank you. You have a good weekend.
Yeah, you too. Take care. Okay, and for you guys out there in Zoom, I'll be signing off.